No, these are all colored chalks. Oh, I think both are colored chalks.
White.
White.
Yeah, before I just have
That's white chalk, right?
White.
Okay.
That white on the bottom.
Okay, that's totally fine. Where did you get it from?
What did I say?
Oh, I see. Yeah, are there questions? Yeah.
But I was thinking that GSO projection was needed because in the end we wanted to have this supersymmetric theory, right? But last time you explained that that GSO was needed because of this modular invariant, but you used to be showing argument on torus and plane.
Yeah.
Like, but can we just starting from the modular invariance requirement? Can we just show that if we have the modular invariance, we are guaranteed to have supersymmetric?
No, that is not true. No. Because there are examples of modular invariant theories with fermions which are not supersymmetric.
What step things go wrong? I mean, this condition which you take, for example, the antiperiodic requirement will give rise to periodic and all the sectors.
Yeah. So that will only tell us that there should be that if you introduce the world sheet fermions, then it should be take type 0 theory, right? In type 0 theory, what happens is that you project simultaneously in the left and right. Okay, you twist both left and right. So then there you have NSNS sector and RR sector, but no RNS sector, right? So that clearly shows that from the space-time perspective, they are all bosons, right? Yeah, there are no fermions, right? So there cannot be supersymmetry. So type 0 theory is just an example of theories where you have world sheet supersymmetry, you have fermions, modular invariance, but no space-time supersymmetry.
Are you saying the GSO projection is the kind of the only way to get the modular invariance as well as the supersymmetry? Or
that is the only known way. Yeah. Because in order to create a spinor representation, right, you need some kind of Clifford algebra. And Clifford algebra comes from the fermion zero modes, world sheet fermion zero modes. Any other question? Okay. So today we are going to discuss heterotic string theory. And here I am going to use this observation that we made last time, that the spectrum factorizes between left and right except for the momentum. That for any given momentum state, right, you can independently create states using the left moving and right moving oscillators. Okay. And the constants also can be imposed separately on the left and right moving sector. Okay. So this suggests a new way of constructing string theory, which is that we take bosonic string theory on the left, and fermionic string theory on the right. Okay, or let me just say superstring. This is the one that you have been considering. Okay. And this immediately suggests a puzzle. Okay, and the puzzle is the following, that while the spectrum, as you said, factorizes between left and right, so you can do independent things on the left and right. Okay. In the zero mode sector, in the momentum sector, it doesn't factorize. Okay? And the momentum comes from quantizing the zero modes of x mu. Zero modes of x mu lead to k mu. Okay? And in this sector, it doesn't factorize. Right? You cannot choose independently left and right moving momenta. So the way we avoid it is the following. So first of all, on the right, we take x mu psi mu and ln gn constant. Okay, so this is the analog of superstring. And on the left, so this is for 0 less than or equal to mu less than or equal to 9. Right? That's the superstring. Okay. And on the left, we take x mu, okay, still mu running from 0 to 9. Then a C tilde equal to 16 chiral CFT. Okay, it's chiral because C is 0. Okay, the central charge, okay, is non-zero on the left, but 0 on the right. Okay, and the usual ln projection and ln constraints. Is this clear? Okay. Because if you recall what I had said earlier, is that we can define a consistent bosonic string theory in 9 plus 1 dimension by simply compactifying 16 of the dimensions. And compactifying 16 of the dimensions means that you choose a appropriate, a well-defined CFT with central charge 16 on the left and 16 on the right. Okay. Now you are saying that you don't worry about the right at all, right? You don't need anything on the right, but you need to find a CFT with central charge 16 on the left. Okay. If you can find such a thing, then you combine that with 10 x mu's to get a theory with central charge 26. So total C, so total C tilde will be 26 plus 10, sorry, 16 plus 10, which is 26. And then you will be done. Is this clear?
When you say that the things on the right and things on the left, so the operators on the right are just functions of z or z bar, whichever is the right and left.
Yeah, right is a function of z, exactly. Right? But they are coupled through the x mu's. So the vertex operators can be thought of as a product of vertex operators on the which are functions of z, then vertex operators which are functions of z bar. But the e to the I k dot x depends both holomorphic and anti-holomorphic coordinates. Is that clear?
Yeah.
Any other question? So the challenge here is to find a CFT with C equal to 0, P tilde equal to 60.
How is it different from just a supersymmetric theory on the right with just 10 minimally coupled bosonic rings?
with supersymmetric theory on the right. Supersymmetric theory on the right is x mu and psi mu.
That's just, or that was traditional, that is as previously we have.
Yeah.
We just added 10 more extra bosonic fields, which you
Yes.
see on the left.
Exactly.
That is just, we can just take the supersymmetric theory originally we had already, and just add 10 more bosonic fields.
No. See, x mu is both on the left and right. It's not x mu you write on twice. Once you have added an x mu, right, it contributes both to the left and right, because in the zero mode sector they don't factorize, right? So these are the same x mu's. This x mu and this x mu is the same. Okay. So the net worldsheet content is that you have 10 x mu's, right, which are not chiral. Right? Then we have 10 psi mu's, which are right moving, right, which are right chiral. Okay? And then on top of that, you have a CFT with C equal to 0, C tilde equal to 16. That's the worldsheet matter content. Okay? And the projections will involve now only the ln and gn on the right, but only ln tilde on the left, the ln tilde. Okay, because the left sector is like the bosonic string, right? There is no no extra constraint other than ln tilde.
For this you can't use compact direction.
For which?
This C tilde. This additional CFT cannot be a compact coming from some compact.
Well, by definition, it's compact, right?
It's some internal.
It's some internal CFT.
Compactification of space state.
No, because that will have both left and right. Exactly. The usual compactification of space-time will have both left and right.
On the left also there is no psi mu.
On the left, there is no psi.
You write an action like action for this theory where we psi minus psi plus mu because something we put psi minus equal to 0.
Yeah, you can still do it because action for psi plus and psi minus decoupled, right? Because, yeah, there is psi plus, if you remember, it was psi plus del v psi plus integral plus psi minus del u psi minus, right? So you are just setting the psi minuses to 0, right? So you can still write an action for the psi plus. Okay. And I should have said, which I didn't say earlier, is that the CFT for a given psi plus has central charge half. Okay. Each x mu gives central charge 1, 1, right? On left and right. Okay. Each psi mu gives central charge 0, half or half 0, depending on whether it's a left mover or right mover, right? So psi plus mu, for example, will give for each mu, psi plus mu, this gives a central charge of 0, half. Okay, this you can explicitly check. So each psi plus gives central charge 0, half, and each psi minus mu gives central charge half 0. So in the case of superstring, the total central charge from the matter is 10 plus 5, right? That is 15. And that gets cancelled against the central charge of the BC and the superhosts, right? Which we will introduce later. Okay. So this observation gives you one way to construct this C equal to 16 CFT. Okay. And that is to add 32 fermions. Right? 32 left moving fermions. If each fermion gives the central charge half, then 32 left moving fermions will give a central charge of 16. So we add to the worldsheet action. integral d u dv sum lambda, let me call it lambda I del u lambda I sum over I equal to 1 to 32. Lambdas are Marana-Weil spinors. The left moving. Okay. So psi mu in the previous notation, psi mu will only have the plus component now. Psi plus mu 0. Okay. There will be no psi minus mu. Okay.
That's also time is just lambda. These are 2D spirals.
2D spirals, yeah. Right. So 2D Marana-Weil is one component, right? That's why the psi mu is also Marana-Weil. Right? It has only the right moving component. Right? And lambda I will have the structure 0 lambda. I am using the same symbol, right? Because this is what will be relevant for us. There is 0 is just 0, right? We don't worry about that. So I'm not going to write plus or minus. Right? I'll just write it as 0 lambda I.
This is to get the lambda part is to get the theta equal to 16.
Yes.
And then on top of that you have the x mu at the side.
Exactly. Yeah. That's right. Right. So the net content, let me write it again. So net worldsheet matter content is x mu for 0 less than or equal to mu less than or equal to 9, psi plus mu with 0 less than or equal to mu less than or equal to 9, and lambda minus I for 1 less than or equal to 9 less than or 32. Okay. And you can easily construct the action from here. Okay, x action is the standard action. Okay. Psi plus is just this part, right? No psi minus. And lambda action will be this, right? So that forces the equation of motion, forces del u of lambda I to be 0, right? Which in turn means lambda I is purely antiholomorphic, right? Once you go to the complex coordinate system. I index is from 1 to 32, right? Because you are adding 32 fermions. So it has a chiral CFT. This is a chiral CFT with C tilde equal to 16. X mu is on the left. Yeah. So those are the ones that I'm going to replace by these lambdas. Right? So they are not there. Right? So you think of this as if, so when I said that it's half, yeah, that when it's half fermionic, half bosonic, right? The bosonic part you think of as first compactify 16 number of dimensions, right? So that you have an internal CFT with C equal to 16, C tilde equal to 16, right? But now you only want to keep the right moving part, sorry, left moving part. So you forget about the C and we need a CFT with C tilde equal to 16. And that CFT you are getting from the lambdas.
So there's like a mapping between the extra x's and the lambda.
No, you don't need a mapping because in a general compactification, right, the internal CFT doesn't even have to have a geometric interpretation. Right? As long as the total central charge adds up to 26, you have a valid string compactification. Right? Like we discussed the case of, say, 22 copies of the Ising model. Sorry, 44 copies of the Ising model will give a C equal to 22. Right? That you can use as a compactification or compactification. Right? So it's not necessary that these lambdas have to be reinterpreted in terms of x's. Right? Although we can do it, right? Maybe I'll discuss this later, right? But at this stage, these lambdas are just some formula fields, right? It's easiest to construct the CFT using fermions, chiral CFT using fermions.
Amplitude is 32 half objects, 0 half objects in the left sector, right?
Yes.
But we don't, I mean, we could have added a matrix Bij over here. That will not change anything.
Yeah, Bij we can probably absorb inside the lambdas, right? You just rescale the lambdas, right? Or make a linear transformation to make Bij trivial.
There's only a quadratic term.
Yeah, it's only quadratic term, right?
But why did you have to add Majorana while, I mean, couldn't you have arranged 32 with something else? Sorry, 16 with something else?
16 with something else. You could, I mean, you can try, right? But the point is only known CFTs can be constructed from here.
Discrete spectrum. That's the also condition.
No.
That's also not.
That's not, we are demanding that here.
But if we had continuous spectrum, we'll start interpreting as some dimension.
True, but you cannot get a continuous spectrum CFT. Right? What will you do? You cannot use an X mu, right? We know that you can get continuous spectrum if we had an X mu. But X mu will also contribute to the left or to the right. Right? So that is not an allowed thing, right?
Even this Liouville thing.
Even the Liouville theory also has both CL and CR. Exactly. Okay, so in this case,
Even if there was, we don't want that interpretation.
true. Even if there were, we don't need that. We don't want it, right? But what I'm saying is that in this case, that is not even a choice. Is this clear? Okay, so these are dimension half. Okay, same argument as the size, right? Size were dimension half. This is also worksheet fermion. Okay. So these will be dimension 0 half. Okay, these are dimension 0 half. So I'm basically going to drop the minus. Okay, we'll call them lambda I. These are dimension 0 half. And this means that by the same, following the same logic that I gave last time, that you have to sum over both Ramond and Neveu-Schwarz of these fields. Right? You have to sum over both periodic and anti-periodic boundary conditions. Right? You have to include the different sectors. So need NS and R sectors.
Supersymmetry does not act on it.
No, worksheet supersymmetry is only on the left hand side or only on the right hand side. Right? Again, if you want to see where it comes from starting from a gauge invariant action, right? Basically, this comes from again local worldsheet supersymmetry. Okay, but that local worldsheet supersymmetry now is chiral, right? It only acts. So the gravity law, for example, doesn't have two components. It has only one component, okay, chi plus, which is in the holomorphic sector. Okay. So because you have only chi plus and not chi minus, when you take the equation of motion for chi plus, you only get one constant, not two. Right? Earlier I had said that the constants that the Gn and G tilde n, right? They are coming from taking the derivative of the original gauge invariant action with respect to the worldsheet gravitational fields. Okay? And there we had both plus and minus components. Gravitationals were two components. Now the gravitationals themselves are one component. Okay, and that's the reason why you get only Gn and no G tilde n. Because the worldsheet supersymmetry also acts only on the right sector, not on the left sector. From the lambda. Yeah, the same argument. Exactly the same argument that I gave last time, right? Also applies to this.
These will contribute to L and tilde.
It will contribute to L and tilde, indeed. Now,
Can I say?
the next constant, which is that these boundary conditions have to be chosen so that we have modular invariance. Right? Because that's one of the reasons why you have to include both sectors. Right? As you saw, if we didn't go to the torus, right? If you are only restricted to the plane, you could have lived with only NS sector fields, right? Because the OPUs will close, right? But on the torus, I mean, once you demand the modular invariance on the torus, you need both sectors, right? But it's not just enough to say that you need both sectors. You have to make sure that the amplitudes are modular invariant, right? They don't change under this exchange of two sigmas, sigma 1 and sigma 2, or other diffeomorphisms. And it turns out that this constraint gives only two independent choice of GSO projection. You cannot get more than one, more than two, right? If you want a modular invariant theory, there are only two ways you can get it. Okay. So typically what happens is that when you take the torus partition function or torus amplitude and make a modular transformation, you pick up a phase. Okay. And then you have to demand that that phase is one. Okay, and demanding that that phase is one, you get restriction on what kind of boundary conditions you can put.
In a priori, we didn't know this. In the filter,
A priori, you didn't know this.
the 32%.
Yeah, you could have, for example, taken each lambda I, right, to be NS or R, and summed over all those possibilities.
That's
Right?
one possibility.
That's one possibility. You can mix, exactly.
Out of this, the 32 possibilities, there's only two.
Yeah, exactly, yeah.
So you mean two as a combination, right? All could be either NS or something.
Yeah, exactly. Two as a combination, right? So I'm going to describe what those two are. Yeah, these two are the 8 cross here and SO32. So GSO projection, choice 1. Choice 1. All lambda I periodic or all lambda I antiperiodic. Okay? So only two sectors. Everything is on the left, yeah. On the right, you have the standard GSO projection, right? Yeah, all the psi mu's periodic or all the psi mu's antiperiodic. Okay, those will give the NS and R. So this sector means that on the left also, we have two sectors, NS and R. Right? All lambda is periodic will be R, all lambda is antiperiodic will be NS. Is this clear?
This was not expected from Lorentz invariant, right?
No, because in this case, that these are, Lorentz scalars, right? I's are not Lorentz indices. So certainly Lorentz invariance is not in play here. Is this statement clear? So what does it mean? What kind of identification are you making in the field space? In the configuration space, if you think of x mu, psi mu, lambda I, right? This is identified with something, right? One is you can change the sign of psi mu, right? That was the GSO projection on the right. Okay. What does this mean, right? The fact that you are including both periodic and antiperiodic. What kind of identification? This will be identified with what? Yeah, this should be x mu, psi mu minus lambda I. All the lambda is change sign, right? Because this, if you make this identification, right, then a closed string can either connect x mu, psi mu, lambda I to x mu psi mu lambda I. That this is sigma equal to 0, sigma equal to 2 pi. Right? This is one choice. Okay. The other choice is that sigma equal to 0, you start from here. And this goes to sigma x mu psi mu minus lambda I, because this is the same point in the field in the configuration space as this one. Okay, so these are the, so this will be the Ramond and this will be the NS. Pardon? In this case, there are no open strings. Right? Open strings come only in the presence of d-branes. Right? So you have not introduced d-branes yet. Right? We will do the d-branes later. In any case, heterotic string theories don't have d-branes. Yeah. So that choice I am not writing. Right? So because that will give the on the right sector whether it's NS or R. Yeah. Right now I'm only concerned on the left sector. Right? Otherwise, you can change the psi mu. Right? That will be the Ramond on the right sector. Why not? I mean, in the configuration space is a field configuration space that contains everything, right? Yeah. So GSO in the field configuration space, this point in the field configuration space is linked to that, and this one. Right? So this is saying that the psi mu's are periodic, right? Which means it's the Ramond sector on the right. Right? But psi mu's could be independently antiperiodic. That will be NS sector on the right. But independently of that, you have these two different possibilities, right? Which are NS or R sector on the right, on the left. Is this clear? So in this case, what will the GSO projection do on the left? GSO operator, right? What kind of projection do you have to do? Under what symmetry it should be invariant? See, once you have made this identification, no? Yeah, all the lambdas goes to minus lambda. You have to make sure that all the states are invariant on that kind of transformation, right? Yeah. So which means that if you have a state which is even parity, right, then you can only apply even number of lambda oscillators to get a state with even parity, right? Starting with an even parity state, a lambda oscillator acting on the state will give an odd parity state, right? So that should be projected out. So GSO projection is a Z2 projection, right? There is a Z2 symmetry and you have to demand that it's invariant under the Z2 symmetry. Again on the left, right? On the right side there is separate GSO projection. Is this clear? So this is called.
Z2 is out of the Z2 to
This is one particular Z2 out of Z2 to 32. One combination, right? That which we are using to make this identification.
And okay, what is the argument that out of this 32 Z2s, there is only two consistent choices of Z2s?
Modular invariance. So when you construct a partition function, right, you will find that the partition function is not modular invariant unless you impose one of these two choices. Yeah, I'm going to describe the other choice. Right? But let me just give the name of this theory. So this is SO32 heterotic. Yeah. So what is SO about it is, you can guess what is SO about it. Okay, what is 32 about it? 32 lambdas, right? So what is a group of symmetry?
So you're saying this as an SO.
Yeah, here is SO32 symmetry. Lambdas are real fermions, right? It is a Majorana file. So you cannot use SU, right? You cannot use a complex valued matrix. So SO32, right? O30, okay. O is, it's not actually, it is not actually, the theory is not O32 invariant, right? It has a different, the full group structure is spin 32 mod Z2, which we will come to later, right? Depends on what kind of states you have. But at least locally, the algebra is SO32. Yes?
This sounds like a very natural choice. What other choice can you get?
Yeah, so he is saying, okay. Yeah, there is one more choice. That's the second Z2 out of this 2 to the 32. So choice 2 is divide lambda I into two sets of 16 each.
The choice of sets is up to me.
Up to you, yeah. It doesn't really matter because all lambdas are equivalent, right? So let me call this chi and eta. So chi A and eta A running from 1 to 16. Right? 1 to 16. So each set contains, okay? Then the identification that we make is x mu psi mu chi A eta A is equivalent to x mu psi mu minus chi A eta A, and it's equivalent to also x mu psi mu chi A minus eta A. Okay, there's also, of course, you can change psi mu. Okay, that I'm not writing, just is only in the left sector. Okay. And by composing these two, you also have the other identification where you change the sign upward. Okay, x mu psi mu minus chi A minus eta A. Is this clear? So this is a Z2 times Z2 identification. That you have picked two of those 4 generators out of the 2 to the 32. Okay, Z2 times Z2 identification.
Going simultaneously minus,
Yes,
like if you write it like this, that's in the boundary condition.
yes,
So periodic gave us Ramon, anti-periodic gave us Navier.
yes.
Here you will get
Yeah. Now say, yeah. Here you will get Ramon Nebel-Schwarz, or on the left. So Ramon Nebel-Schwarz, Ramon, and Ramon. Besides that, you'll have R and NS on the right. On the right. Yeah. So 2 to the 8, so 8 combinations altogether, right? Not 2 to the 8. 2 to the 3. Yeah, you put by comma, right? RNS, right?
no other.
Sorry, the other way. I have to write the RNS. You use a semicolon to comma, separate out left and right, right? So on the right is R or NS, right? Here you write R or NS, right? Depending on whether it's whether chi or eta is antiperiodic. Doesn't matter, right? You make your convention. If you want to, well, you can add label L and R, right? But both are coming from L. L1, L2, yeah, L1, L2, and you write L1 first and then L2. Yeah, this is supposed to be 8 cross 8. Why is it 8 cross 8? Why is it 8 cross 8? Anybody has any answer? What would it be? If you had a choice, if you just looked at this, right? What would it be? What do you call it? Yeah. Yeah. So you would call it SO16 times SO16, right?
Then somehow it's not available.
Yeah, it's mixing also because there are some
Yeah, there's a mixing.
No, then there's no mixing. Because you can only independently rotate. Because otherwise the boundary conditions will not be preserved, right? SO16 times SO16. Yeah, that's a subgroup of E8 times E8. Okay, because E8 has a subgroup which is SO16. Okay. But still doesn't explain why it's E8 times E8. Yeah, so we'll see why it's E8 cross E8, but that requires analyzing the spectrum. Yeah, there's some hidden symmetry, right, which you'll only see later. Okay, when you analyze the spectrum.
So here we get GSO as Z2 cross Z2, right?
Z2 times Z2. And there's a Z2 separately on the right sector. Yeah.
Z2, GSO left.
Exactly.
Z2.
Yeah, Z2 times.
But there are no other choices that you are saying will come from the modular invariance or.
Exactly.
For example, we don't have Z2 times 4 times Z2, right?
Yeah, you don't have that because that will destroy modular invariance.
In the type 2 theories we were doing, you said the NS sector, that is left and right. There the vacuum gets set, the GSO parity of vacuum is unambiguous because there are some hidden ghosts acting.
Yeah.
And then in RNS, NSR and RR we had a choice to be made.
Yeah.
And we made a choice and then that differentiates type 2B and type 2A also. Here also, do we have a choice?
No, here there's no hidden host.
So we
Because we are on the left sector, right? There's no beta gamma host here. BC ghosts don't carry GSO parity, right? Yeah. Yeah.
Of declaring vacuum to be.
No, now we have no choice. The vacuum is GSO even. In this theory, we could declare, but there's no hidden. I mean, ultimately, SL2 or invariant vacuum of the whole system, we would want to be GSO even.
Because you want that to be a physical state.
Well, SL2 or invariant vacuum by itself is not a physical state, but many of the manipulations require that is an allowed, yeah, GSO even. That may not satisfy the correct host number condition or the Ln condition, etc., but that should be at least in the cohomology, right? Not in the cohomology, in the initial Hilbert space.
That should not be ruled out by the.
That should not be ruled out by GSO projection. Okay, so in this case, the vacuum will be GSO even in the left sector.
Last time we differentiated between getting the space supersymmetric theory and the modular invariance theory, right? You said that we have two choices because of the modular invariance, but they both lead to supersymmetric versions theories also, right?
Yeah, but we could have had other choices, right? Last time, for example, if we type 0 is a different choice, right? That also gives modular invariant theory, but it breaks space-time supersymmetry, right? Here, on the right, you have fixed what you want to do, right? On the left, we are looking for a C equal to 16 CFT, right? Which is modular invariant, okay? And that puts a strong constraint on what kind of theory you can have. Okay. And the reason is basically that when you construct the partition function, right? This is a purely left moving sector. Okay. So its partition function will be a function of tau bar only. Okay, not a function of tau. Okay. So you're asking for a function of tau bar to be modular invariant, right? Or modular covariant. It can pick up some factor which will cancel with something else. Okay. But that once you have anti-holomorphy, right, holomorphy, then the number of modular invariant functions get highly constant. Okay, that's the reason why you have only two choices.
But if someone is interested in, let's say, non-supersymmetric theories in the end,
Yes.
But heterotic versions of it,
Yes.
we can still get it, right? It would be modular in.
We can get it. Yeah, there are ways to construct such things. One is called O16 times O16 string. Yes, it is possible to get such theories, right, which is not supersymmetric but modular invariant.
So this is not like you said, out of 2 to the 32, only 2 are modular.
But supersymmetric. If you allow non-symmetric,
Then you have to mix left and right. You have to somehow mix left and right. That's like type 0, right? Type 0 is modular invariant. You are mixing left and right. If you want a chiral partition function, right, which means it's a function of either tau bar or tau, right? And if you demand its modular covariance, that's a highly restrictive condition.
There are only these two chiral CFTs which centers as like
60,
600
yeah.
160.
Exactly,
That's
exactly, yeah, with the right property.
non-supersymmetric, then we can mix the DSO projection to act on both the left and right simultaneously, then we may get.
If you, yeah, exactly, yeah.
How many generators E8 has?
248.
Minus 16.
SO16 has 120,
Oh,
right? We need a lot more generator. Yeah, it's a wild enhancement. But we'll see how this thing comes. Okay. So quantization now is straightforward.
So the two choices that you mentioned, we are always identifying psi mu with psi mu. If we also had identified psi mu with minus psi mu, would that
Yeah,
not
so
be
that's
the
an independent choice, right? That's an independent identification. So here, for example, we have 4 different configurations which are equivalent, because you can independently change the sign of lambda or change the sign of psi mu. Okay? Because psi mu I'm not writing because that's a choice in the right moving sector, right? That identification is always there.
okay?
Similarly here, independently of what you do in chi and eta, you can also change the sign of psi mu.
Okay.
So there are 8 different configurations which are all declared to be the same in this case.
Okay.
Okay, that's the reason why the number of sectors in Ashoke heterotic, there are 4 sectors, because you can choose separately Ramond or NS on the right and Ramond and NS on the left. In the E8 cross E8 heterotic, there are 8 sectors, because you can choose independently Ramond or NS on psi mu, Ramond or NS on chi, and Ramond or NS on eta. So the psi mu identification I have not written because that is the same as in superstring. Any other question? So quantization. I think it doesn't have a tachyon, but at one loop, you start generating a dilaton tadpole. Yeah, because O16 times O16 is better than the type 0 theories, in the sense it doesn't have tachyon, right? But at one loop, you generate one tadpole, right? And that creates trouble. So it's consistent string theory, it just doesn't have a perturbative vacuum. Because once you have a 1-point function of a massless scalar, right, then the potential has a linear term, right? And there's a quadratic term to balance it, right? So you don't know where it's going, right? It just runs away. Unless some higher order correct terms can balance it, but that you cannot study within weak coupling approximation, right? Any other question?
When you say one loop, this whatever you were saying, it means that the expectation value of this vertex operator on a torus is non-zero.
Exactly, yeah.
Okay.
Now the dilaton vertex operator on the torus is non-zero. Sorry, you had a question? No, I'm not. Otherwise, I cannot explain why E8 cross E8. I will do more than more than this. Okay. So by straightforward, I mean you just write the corresponding oscillators, right? Okay. So let's take SO32. SO32 has psi mu oscillators, which we call B mu minus R, right? B mu R. And R is integer plus half, depending on which sector you are considering. Similarly, we have lambda I oscillators. Let's call them dir. Okay, and again R is integer in the Ramond sector and half integer plus half in the NS sector. So a generic state we have the form product over mu n alpha mu minus n to the power q mu n product over mu n alpha tilde mu minus n to the power r mu n, and then product acting on the Hawk vacuum, which carries momentum k. Right? K is 10-dimensional momentum. Okay, because x mu's are 10-dimensional. Tilde on d, yes, okay. Tilde on d. Pardon? Yeah, we are doing old covariant, right? Ghosts haven't come. Because even in Superstring, we didn't introduce any ghosts. Okay? And then on this, you have to put LM, GM, and L tilde M constant. Okay, namely that they will vanish for M greater than or equal to 0 and R greater than or equal to 0.
Still gives no more special treatment.
Yes, 0 modes of x mu. That is in the fact that the k mu, k doesn't factorize. Yeah, we have to. Whenever R is 0, right? Whenever S is 0, you have to give it special treatment. Special treatment means it will be a Clifford algebra, 32-dimensional Clifford algebra.
That will also give space-time.
No,
That will not.
that will not be SO32 spinor, not space-time spinor, right?
Only the psi mu gives space-time.
Yeah, only the psi mu gives space-time spinor. Okay, why is it confusing you?
So pairing R and NS in lambda does not change bosonic or fermionic.
No, it doesn't.
So the space-time will also
That-
be supersymmetric.
Pardon?
Space-time supersymmetry
Yeah.
will only mix psi.
Exactly.
R and
Space-time supersymmetry is going to come purely from the right moving sector. Right? Because right moving sector, NS corresponds to bosonic, R corresponds to fermionic. Right? That's why we discuss this factorization. The supersymmetry also comes separately. You remember type 2 superstring, it comes separately from right and left. Right? That's why it has n equal to 2. Okay? Now there will be supersymmetry only from the right moving sector, right? But not from the left moving sector. So number of supersymmetries will be half of what we had earlier. Right? It will be n equal to 1 supersymmetric theory. Is clear?
Constraint over some over U and V no this time.
Yeah, we have to. L0 and L0 constant. L0 and L0 tilde constant, right? These are the ones which give the Marshall condition.
GSO even.
Yes, GSO even, yes, indeed, right? So GSO even is, yeah, it has to be invariant under GSO.
Because the right sector will again go the same way, right? For example, B under -1 to the power FR, B will just change sign, right? B
B will change sign. right? And -1 to the, yeah, so right sector will be exactly the same, right? We are not going to touch the right sector. That part will be exactly the same as what we did earlier. Yeah, you have to hold left GSO also, right? So left GSO is the one that you have to worry, right? So we have this condition that sum over n q mu n plus sum over sum over r u mu r mu. Is equal to C. And alpha prime k square by 4 plus alpha prime k square by 4 equal to C. Right? C is the normal ordering constant.
Can you say it also? I mean, last time you said in NS is minus half. What is? How do you fix this constant in heterotic?
Yeah. Again, it factors between left and right.
Yeah. So you already know the answer.
You already know the answer for C. Yes? Yeah. So C is minus half in NS and 0 in R. Vacuum, right? C tilde.
In the left sector.
Left sector I have not said anything. The only right sector. Right? I can also specify the left sector. So left sector is sum over mu n plus sum over I and S I think this should be, let me just, it's plus C equal to 0. I think that's the way I had to put it, no? Plus C equal to 0. And this is minus half in NS and 0 in R.
We find L plus C is equal to 0. That's why you're saying plus C.
Yeah, yeah. And C was minus half for NS. Okay, maybe, yeah. Maybe this C is not the same as what he used for C in the earlier class, but this, once I have given the value of C, there should be no confusion, right? The way to check this is that if you did have the NS sector vacuum, right, it should be tachyonic. Okay? And here, K square will be positive, right? If you had no oscillator, right, then this condition will put K square to be positive. Positive K square means negative mass square, right? Because K square plus M square equal to 0. Okay? So it will give a tachyonic state. I think this convention is what I used last time also, right? The L0 plus C.
I think previous class.
Okay, previous classes, okay, maybe. Okay. Okay. Okay, yeah, spectrum also. So just correct if there are any errors, just correct it, right? This is the statement. And so here you can plus C tilde equal to 0. This C tilde has the same value as the bosonic string theory in the NS sector. Because NS sector is like the SL2R invariant vacuum. Okay, SL2R invariant vacuum comes in the NS sector, if you remember, right? Yes, yeah. Yeah. You recall just what we did last time, right? NS sector, right? is the one which contains SL2R invariant vacuum for the psi mu's. Because I said last time that if you apply L minus 1, right, on the NS vacuum, you get 0. If you apply L minus 1 on the Raman vacuum, you don't get 0. Right? This is something you can explicitly check by from the expression for the LNs. Right? So the SL2R invariant vacuum is in the NS sector. Okay. So the NS sector here will have the SL2R invariant vacuum, right? And in the NS sector, right, which has the SL2R invariant vacuum, this will be like the original bosonic string theory. NS sector of the original boson, the SL2R invariant vacuum of the original bosonic string. -1. The original bosonic string theory has C tilde equal to -1. Right? That will be exactly the same in this case.
Because you have the SL2R invariant vacuum fine.
Yes.
After that what?
And so whatever logic, right, gave rise to C tilde equal to -1 in bosonic string theory, right? The decoupling of the unphysical state. The same logic, I mean, now you are going to apply that same logic on the on this theory, right? Independently on the left sector. That will give you C tilde equal to -1 in NS sector. And it will be 1 in the Raman sector. This is not obvious. You have to do some calculation to check this. Again, I mean, one way to do this is that you have to look at the decoupling of the unphysical states, right, in the Raman sector, right? There is another way to do this, which is uses the zeta function regularization. See.
And then do the normal ordering sum.
Yeah, we do the normal ordering sum, right? That's the way.
Can we just impose exactness and closeness of QB and get it?
Yeah, but I have not introduced QB, right? Once you introduce QB, yes, you can get it from there. Okay, if you want a shortcut, you can use the zeta function to get this result, right? Because it will be sum over R with R half integer versus integer, and that will give the result. In this case, in fact, it's not hard to figure out why it's +1, because bosons and fermions, right? The only difference between bosons and fermions will be that the ground state, the harmonic oscillator ground state energy is half h bar omega for bosons and minus half h bar omega for fermions. Okay, and there are equal number of bosons and fermionic oscillators effectively, and that's what is responsible for the net thing being -1. It's basically controlled by the central charge. Okay. But if that is confusing, don't worry, right? I mean, this is the answer. C tilde equal to -1. Okay, there are many ways to get there.
The reason it varies between NS and R sector is because whatever QB and all will also have this fermionic fields and
exactly.
boundary conditions.
Yeah, their mode expansion will also change, right?
The action itself will change.
Yeah, exactly. Yeah, their action will change because the QB has all the modes, right? The G's. QB can be written as C minus that. It has the it can the explicit details on the modes are not important, but just like in bosonic string theory, QB contains the LMs, right? It could be written, matter sector information came through LMs. In this case, the matter sector information will come through LMs and GMs, right? And G's have different okay, so let's see, given this, what we can learn. Now here you see, let's suppose that we set this equal to 0. Okay, all oscillators 0. The vacuum is GSO even, right? Yeah, that you are demanding. Vacuum is GSO even. So we get from NS sector a tachyon. So NS sector on left has a tachyon. Apparently has a tachyon. Same as a bosonic string case, right? You don't look happy. This statement is clear or no? This is the state K. Take the state K. Okay, that satisfies the GSO projection on the left. Apply this with C tilde, and these are all 0. Apply this with C tilde equal to -1. You get a tachyon. Right? So what happens to this state? Why is the theory tachyon free?
Where is the theory tachyon?
Free.
Bosonic theory added it.
Yeah, so this is giving that there is a tachyon, right? But the claim is that this is a good theory without tachyon. Pardon?
Maybe can we not find that, but we can find consistent right oscillator for it.
Can you?
Looks like it's just 3 by 2.
Right oscillator is like fermionic string, superstring, right? Right sector is like superstring.
Can have, oh, there's no 3 by 4.
So that's 3 by 2 oscillators. Okay.
That's
Yeah, so if you put alpha prime k square by 4 as 1 there,
Here, alpha prime k square by 4 equal to 1.
that thing to be minus half, which is not possible. The integer sum to be minus.
so there's a tachyon in the right and the left, right? In both there's a tachyon because sequence minus half say there's a tachyon and then there's a -1 here and there's a tachyon.
Okay, but that will not work because this both conditions have to be satisfied, right? Alpha prime k square by 4 cannot be both -1 and -half, right? Okay,
So there the
but yeah, but this is also GSO odd. The vacuum is GSO odd on the left sector or the right sector, right? So you cannot just set all of these to 0, right? That's a GSO odd state. You cannot set it to negative integer also. Exactly. So on the right, right, this condition can only be satisfied by taking this sum to be half. Right? That's the minimum that you can have. Because the vacuum is GSO odd, right? So you can put a B mu minus half on the vacuum. That will be GSO even. Okay? But that will cancel this minus half, okay, and will give you alpha prime k square by 4 equal to 0. Right? So just the constraint on the left, right, tells us that you cannot get any physical state with alpha prime k square by 4 less than 0. Sorry, larger than 0. Yeah, larger than 0. Right? So alpha prime k square by 4 must be less than or equal to 0, which means that the states must have mass square larger than 0. Right? So even though the left sector allows apparently tachyonic states, okay, because the same k has to satisfy both conditions. Right? This is the reason I said that it factorizes, right, except in the zero mode sector. Right? You don't have separate KL and KR. Otherwise, you could have said KL satisfies this, KR satisfies something else. Right? That possibility doesn't exist. The same K has to satisfy both conditions, and hence we cannot have the tachyonic state. Level matching, indeed.
That is saying that you can't switch on this VI mode from D tilde mode.
No, it are there, right? I mean, the full string theory contains both left and right. If you switch on see, even if you could, it wouldn't help. Imagine that the ground state was here. That's what I did. Right? So that means, yeah, you cannot do it. Right? Yeah, there is no state where these have been switched off completely. Right? Even though the ground state was GSO even. Yeah, exactly. So this integer can be 1 if this integer is 1, right? No, that is not GSO odd. In NS sector, that is not GSO odd because these modes are, it is a half integer mode, right? Okay. So you can put 2 lambda I minus half, right?
Oh, in NS, yeah,
Yeah. You can either use alpha minus 1, alpha tilde minus 1, right? That you can certainly do, right? Or d tilde 2, d tilde minus half.
But does it, is it just ruling out this tachyon DNS or is it ruling out other states as well?
No, it's ruling on many other states because you have to have level matching, right? So, yeah, for other states, the point is you have to find appropriate thing on the left and take the product.
So that 2 minus halves, that will be like the SO 32 vector.
No, 2 minus halves will be SO32. Yeah, so what index does each of those oscillators carry? SO32 index. No, I, vector index, right? Yeah.
There will be sum of.
So I and J, right? And it has to be antisymmetric because they are fermionic oscillators, right? So what is the antisymmetric product of two vectors?
Oh, wait, what dimension?
Pardon? No.
Antisymmetric
Any
product-
SON, take any SO2n, right? And take two vectors, take the product, two vector representation, take the product and antisymmetrize. One more vector.
3 dimensions, A cross B.
In 3 dimensions, yes. But you count the number, right? Each of them is n dimensional, right? So what is the number? What is the number of such states? Antisymmetric combination of product of two vectors.
n into n minus 1 by 2.
N into n minus 1 by 2, right? That's dimension of some representation of SON. It's adjoint, right? Adjoint of SON has dimension n into n minus 1 by 2. This is generic. This is not familiar? Okay. Yeah, so n into n, adjoint of representation has n into n minus 1 by 2. So these states will be adjoints. Okay, so let me write down the massless states.
Logic which says that there's no tachyon, please.
Yeah, okay, logic. So you give me a state. You give me a state which looks tachyonic. I'll tell you why it's not tachyonic, why it's not doesn't exist. Yeah. So you just take K, right? This state. This state will have to satisfy alpha prime K square by 4 plus nothing, right? Equal to minus 1. Equal to 1. Okay? But it also has to satisfy the other condition, right? Alpha prime K square by 2, this is from the left. There it's alpha prime K square by 4, would have been half, right? You cannot satisfy both these conditions simultaneously, right? Yeah. So this, in fact, this itself is not correct because this state, if we just take this state, right? This doesn't satisfy the GSO projection on the left, on the right. Because under the right GSO, this is odd. See, right sector is the superstring, right? For the superstring, I had said that the NS sector vacuum is GSO odd, right? So this state is GSO odd. Okay. So the minimum thing that we can do here is to put a B mu minus half. Okay. This will not affect the left side, but right side it makes it GSO even. Okay, this is GSO even. So now the conditions are alpha prime K square by 4 equal to 1. This is not changing from the left, and this will become half minus half plus half equal to 0, right? So K square equal to 0, but you cannot satisfy both these conditions together. This is telling you alpha prime k square by 4 equal to 1, and this is telling you alpha prime k square by 4 equal to 0. Right? So because the same k has to appear in both left and right sector conditions, right, L0 conditions, you cannot allow this state. This state is not part of the spectrum. Is it clear? Right? So this suggests then what is a part of the spectrum. Okay? You have to raise the left moving sector, right, L0 eigenvalue of the left moving sector by 1, okay, preserving the GSO even condition. So what are the possibilities? What can you do? You have to act to some oscillators, right? So give me a suggestion of what you can apply. Di tilde minus half, dj tilde minus half. Minus half. Yeah, everything is being done in the NS sector on K. This is massless. This is alpha prime and alpha prime K square by 4 equal to 0. Anything else that you can do? I'm not trying to construct states that actually satisfy both conditions, right? So what I'm saying is that this satisfies alpha prime K square by 4 equal to 0, right? Okay. If you just had this, then there's alpha prime K square by 4 equal to 1, right? Or I can write it as minus 1 equal to 0. You have to add a plus 1 somehow, right? And you can add plus 1 by applying these tilde oscillators. Yeah, you can also do alpha tilde. So B mu minus half, alpha tilde nu minus 1 on K. Alpha tildes are there, you don't forget them. Sorry, not. Yeah, then this is fine. On the left sector, there is, this is GSO even, right?
What does first state correspond to?
Okay. First, let's start. What does this state correspond to? Second state. What would it correspond to in the target space? This is a graviton dilaton antisymmetric tensor, right? It has two indices, no symmetric condition. Right? So this will give you graviton dilaton antisymmetric tensor. Yes, but alpha alpha in the fermionic string is GSO odd, right? Here,
Comes from a mode of psi and mode of a fermionic worldsheet fermionic and a mode of a worldsheet bosonic
yes,
gives the graviton.
yes, because the worldsheet, whether in the worldsheet it's boson or fermion, right, doesn't control whether in space time it's boson or fermion. The worldsheet, whether it's bosonic or fermionic, controls whether it's GSO even or GSO odd, right? We have made sure that this is GSO even, right? On the left it's GSO even because, on the left it's GSO even because the ground state is GSO even and this is GSO even, right? On the right it's GSO even because the ground state is GSO odd and this is GSO odd. Is clear? Okay, now this state. This is vector in some representation, right? Vector in adjoint representation. Massless. So what are those? Vector fields in the adjoint representation of SO32. Those are gauge fields, right? So these are the gauge fields. Right? So what we learned from here is that the spectrum in the NS sector, NS on the left and NS on the right, contains the graviton dilaton antisymmetric tensor and SO32 gauge fields.
So now we'll see it proceed.
E8 cross E8 will come,
More massless.
yeah, there will be more massless fields. Okay, I can give you a hint that the adjoint of E8, right, decomposes into this adjoint of SO16 plus a spinor of SO16. Spinor of SO16 is 128 dimensional, right? So 120 plus 128 is 248. Okay, so you can try to guess where it may come from. Okay, let's look at the Ramon.
Global symmetry widely become a case.
Yes, exactly. Yeah. So typically global symmetries in the world sheet always become gauge symmetries.
Was there something like this in bosonic case?
If you have a compact direction, right, then the global symmetries in those compact directions become gauge symmetries, gauge fields. Like even just a translation of x mu, right? Those become gauge fields.
Okay. Yeah.
Yeah, that will be 1 to the power something.
Interpretation of compactor and target space and
True.
G mu.
But the same thing may have more than one interpretation, right? Global symmetries becoming gauge fields, that's a universal thing, right? And it basically follows from the fact that if you have a global symmetry on the world sheet, there's an Noether current, right? And you can argue that the Noether current is typically holomorphic or anti-holomorphic. So you take the Noether current product, take the product with alpha mu minus 1 or alpha tilde mu minus 1, and that produces a gauge field.
You take Noether current
And other alpha mu minus 1, if it's a Noether current, left moving Noether current, you take the product with alpha mu minus 1, right?
because, am I sure that this Noether current have mu index because it's a world sheet current?
Yeah, because it's an internal index, internal symmetry, right? Exactly.
Get a vector and hope that it's massless. So I will.
Well, it will be massless because by construction, J mu has a dimension 1, right? So its oscillator will have minus 1 modding, right? And alpha tilde mu minus 1, right? So if you have a left moving Noether current, you tensor with alpha mu minus 1. If you have a right moving Noether current, you tensor with alpha tilde mu minus 1. You'll get something massless. Those will be massless vectors.
Here you bring tensor with alpha mu.
Here asking about bosonic. The analog of alpha in the fermionic theory is psi mu or b mu.
I mean, anything take mu index.
Anything on mu index, yeah. But here, the b mu minus of acting on the ground state is the GSO even state, and that's the one which is the vector, which carries vector like index. Is this clear? Okay. Now take Ramon NS. You are doing NS and so far, right? Make the left moving into Ramon. Okay. As far as the right moving is concerned, nothing changes. Right? In the left moving now, we have the index A. Okay, the spinor index. Sorry, in the right mover. In the right mover, you have the spinor index. This is from the right mover. This is SO9, 1 spinor. You have KA. The condition is alpha prime k square by 4 equal to 0. Because if you recall on the Ramon sector, right, the C was 0. Right? No normal ordering constant cancels. So this alpha from k square by 4 should be 0. Is that clear? Okay. And but so you have to somehow make alpha from k square by 4 equal to 0 also on the left. Right? You apply the same operator. These two operators, right? So here you can have either alpha tilde mu minus 1 or d tilde I minus half, d tilde j minus half acting on k in the Ramon sector, in the on the right part.
Oh, you wanted to add a +1 because there's a +1 in the R sector here.
Exactly, yeah. Right? So you want to raise it by 1 so that we can satisfy with k square equal to 0. Without that, it would have satisfied GS on everything else, but this would be -1, right? It will be 1. So the two things are contradictory. Right? In order that you can satisfy both left and right condition, you have to put these.
Why are minus are there integers? Are
No, sorry. We are considering here. Yeah, NSR. Right sector is the supersymmetric part. So right sector is Ramon.
what is the R?
R level is just saying that this is the right sector. Spinor index of right sector. I don't have to say it actually. Let me write this K. Because anyway, SO32 spinor index will be different. Right? So now I'm writing A, which is the SO9,1 spinor index. It's clear that this is the Ramon sector from the right movers.
Target space adjoint scale.
Target space adjoint spinor. This is IJ provides a scalar, it's a adjoint, right? But there's also A index. A is the spinor in target space, right?
Everything in this sector is fermionic.
Everything in the sector is fermionic, yes. Everything in the sector is fermionic. Okay. So this one you have already seen, right? Or the analog of this one. So this is a gravitino. Because this carries a vector index and a spinor index. Okay, so this is like a radical Swinger field. This one is adjoint of SO32 and it carries a spinor index. So what state is this? Super partner of the gauge field, right? This is a gaugino.
Satisfies the first L0 constraint, but how does it satisfy the L0 tilde constraint?
Yeah, L0 tilde constant, just the same argument as to why these satisfy L0 tilde constant, right? Because this ground state, no, that is when you take Ramon sector on the left movers. We are still taking the NS sector on the left movers, right? So C tilde has not changed. When you go to the Ramon sector of the left movers, then you have to use that +1. Is clear?
That's why we use the alpha tilde minus.
Yeah, we need the alpha tilde -1 to raise that -1 to 0. So you have a gravitino and a gaugino, right? So this basically the spectrum is the same as n equal to 1 supergravity. Spectrum same as n equal to 1 supergravity. In d equal to 10. With SO32 gauge group. N equal to 1 supergravity coupled to okay, and independently of string theory, when one does an analysis of the anomaly cancellation in n equal to 1 supergravity, one finds that this SO32 is one of the groups for which the anomaly is cancelled. E8 cross E8. There are this U1 to the 496 and the E8 times E1 to the 248. Right? Those are there. There is an underlying string theory for those. And as I was discussing that day, there is a recent argument that those things are those theories are inconsistent. Is this clear? No, not at the supergravity level. You have to make some additional assumption that all the branes are consistent in that theory. And then you find that there are branes which are not anomaly free. Anyway, we are not going to go into those, right? We just focus on string theory. Okay. So one last thing I have to say is that we so far considered only the NS sector from on the left, right? R sector on the left. So ground state will be K and some other index, that is the, so what index will it carry now? SO32 spinor index, right? So you have to devise some name for this, right? What do you want to use? Alpha you don't want to use, right? Alpha or yeah, that is true. Okay, let me make F dot. F. Okay, this is SO32 spinor index. Yeah, yeah. Pardon? No, I'll call it now RNS. RNS or yeah, RNS. Yeah, if you take RR, then the A index will also be there. How do you get F index? Because now these modes, the where are those? Yeah, D tilde I modes have integer moding, right? So there's zero mode. Oh, that means there is a Clifford algebra, right? There's the algebra of the zero modes. So when you quantize the Clifford algebra, you get spinor representation of SO32. Dimension of the? Okay, dimension of this SO32 spinor, you can check. To begin with, you have 2 to the 16, right? You divide into plus minus, right? And then you can use a file condition. Okay, so the file condition basically means the number of minuses is even.
Generally, this is complex 2 to 16.
Yeah, complex 2 to 16. We'll have to reduce it. We have to reduce it, right? But first, let's impose a projection condition, GSO projection, right? So GSO projection will half it, right? So it will be 2 to the 16 divided by 2. That is 2 to the 8. Sorry, 2 to the 16 divided by 2. That is 2 to the 15. Okay? So this means that the number of pluses, say number of minuses is even. Let's fix that. Number of minuses can be either even or odd. Number of minuses is even, right? Then by applying a GSO even operator, you cannot change that. Okay, number of minuses is even. Okay. Now you can ask if the complex conjugate is part of the same representation. Right? That will determine whether it's real or complex. Okay. If the number of minuses is even, okay, complex conjugation will make the minuses into pluses and pluses into minuses. Okay. Then number of pluses will be even. Okay. But if number of pluses is even, what about number of minuses? Yeah, total number is even, right? It will remain even. So that means the complex conjugate is also part of this representation, right? So it's not a complex representation. Okay. You take psi 1 plus I psi 2, right? Psi 3, so not psi. Lambda 1 plus I lambda 2. Yeah. These are the zero modes. Okay. So now you define a vacuum, okay, which say is annotated by all of these. Okay. And then you create the other states by applying conjugate operator, right? But you have to use even number of conjugate operator. Declare the vacuum to be GSO even, whatever that vacuum is. You can apply even number of conjugate operator.
16 such operators.
There are 16 such operator. You can apply even number of them. Exactly. Yeah. So you get certain number, right? That's this 2 to the 15. Right? Now you are asking that if the actual number of states, if these are complex fields or real fields, right? Whether they're complex states or real states, right? That's what you are asking. Because if they are complex, then the complex conjugation also you have to include. And what I'm saying is that if you take the complex conjugation of this, right, then complex conjugation is already in that set. Mapping states to, yeah, exactly. So you don't include, you don't have to include the complex conjugation as a new part in the representation. Exactly, right? So as far as the degree of freedom counting is concerned, yeah, you can think of it 2 to the 15 real, right? Where the complex conjugation of this is part of the same representation. Yeah, that's how it goes. Yeah. That's a spinor representation of SO32, right? It better be. If it is a spinor, it better be a representation of SO32, right? Yeah, so even if it's a large number, you cannot do much about it, right? That's group theory.
So these are not massless.
No, oh, these are not massless, yeah. Why are they not? Why are they not massless? You can see from here that C tilde is 1, right? So the L0 condition on the left itself tells us that mass square is larger than positive. Okay. So because since C tilde is 1, L0 tilde and Z S equal to 0 condition tells us basically the alpha prime k square over 4 is less than or equal to -1. Okay, which basically means that alpha prime m square by 4 is greater than or equal to 1. Okay, just by analyzing the left moving sector. Okay. So now if you want to know what kind of states you have, right? You go to the right moving sector and you have to apply large number of oscillators, right? To raise the energy, to raise the L0 till L0 eigenvalue. So you can satisfy this condition. Suppose you take alpha prime k square by 4 equal to -1. Then on the right sector, right, besides these oscillators that you have put, B mu minus half, you have to put one more mode with carrying L0 eigenvalue 1. So you can put alpha minus 1, right? Or a pair of B's, okay, which will be all GSO even. Okay. But these are all massive states. These are all massive states. Is this clear? So these states are spinor representation of SO32 and massive. So this gives us some unique property of this theory, okay, which is the following. Typically in any string theory, even the superstring theories, if you consider a massive state, it decays into massless states, right? Once you go into loop effect, you find that there are always that it's kinematically allowed that it can decay into massless states, okay? And hence those are not stable, right? The only stable states in at least d equal to 10 are massless states. But these states are absolutely stable.
They cannot change sector.
Pardon?
Only massless states are in other sectors.
Yeah, because spinor representation, right? A spinor cannot decay into adjoints and scalars, right?
This is target space scalar. Goes on.
It's a scalar from the point of view of space time SO9, 1. But for SO32, these are spinors, right? And gauge charges have to be conserved, right? So if you have a spinor representation of SO32, right, there is no way it can decay into vector-like representations, right? Because product of an adjoint, right, two adjoints, for example, or adjoint to the scalar, is always in the adjoint or vector-like representation, right? It never generates a spinor.
Like if I had diagonals with SUN,
Yeah.
and quarks in some spinorial,
Yeah,
not in fundamental.
a 6 or whatever, right?
Yeah.
They cannot decay into adjoints.
Just a general.
Yeah,
filter.
exactly, right? A quark, the lightest quark is always stable, right? Because it cannot go into gluons, right? It's basically an analog of that statement, right? So these states are heavy states, right? So not relevant for today's experiment, but they are absolutely stable. Well, if you can, yeah, if you can find them, you will be lucky, right? But this is the general property of these states.
But something like this didn't happen in other type 2 and all.
No, because there, everything.
They had a massless.
Of course, the fermions, right, cannot decay into bosons, but fermions are also in the massless sector, right? There are no massive states. Exactly, gravitinos and yeah, everything could go into gravitinos and gravitons and other things.
So here that statement is not true, which we made earlier, that RNS and NSR give the space-time fermions and that RR and NS.
No. Here, whether it's space-time fermion or boson is controlled by whether in the right sector it's R or NS, right?
So it's simple that R will give fermion.
Yeah, R will give fermions and NS will give bosons. Because the only way you can get spinor representation of SO9, 1 is if the right moving sector is in R, right? Left moving sector, it doesn't matter. Left moving sector, whether it's R or NS, controls whether under SO32 if it's spinor representation or adjoint representation. Exactly. NSR and RR will give fermions, right? Of which NSR will give you fermions in the vector in the adjoint representation of SO32, and RR will give you fermions in the spinor representation of SO32.
Since it's a supersymmetric theory, will the superparticles will also have analogous statement that they cannot decay?
Yes, exactly, right? Because this argument doesn't really care about whether you're considering RNS or RR, right? Because on this side, it's spinor, right, of SO32, as long as you have taken R on the left.
These are space-time bosons which do not decay, and there are some space-time fermions.
Exactly, which also do not decay. Okay, I think that's it. So next time we'll do the 8 cross 8. But let me just give you one information, and then I think you'll be able to solve it yourself. Okay. The C tilde for 8 cross 8. Pardon? RR is the same, right? I just have to make here, I just have to put this A index there, right? Here it will be K, F, and A, right? And then the same argument.
You will get an SO32 and Lorentz spinor.
Exactly. You'll get an SO32 spinor and Lorentz spinor. But by this argument, they'll all be heavy. No massless state in that sector. Okay. So for
They
A,
will be also stable.
pardon?
These RR massive spinor states will also be stable because they
They'll
are
also be
spinor
stable.
in.
Exactly.
Okay.
Right, by the same argument. Okay, so for 8 cross 8, the C tilde is -1 in NS. These are both left. Because left now has 4 sectors, right? Both left, it is -1 in NS is equal to 0 in NSR and RNS and 1 in RR. Okay, these two are probably understandable because NS is like NS of SO32, right? Everything satisfies anti-periodic boundary condition. RR is like R of SO32, right? Everything satisfies periodic boundary condition, right? So the same C tilde. And if it's half NS, half R, it's just in between the two. Okay, that's why it's 0. Yeah, basically it's I mean, if you use a zeta function regularization, right, then it just follows from there that you are just summing over all the modes, right, and only half the modes are like both NS and half the modes are like R, then it gives you something in between.
This R and RNS will just be identical sector wise. So sky and
Well, except that there is a 2 SO16, right?
216.
Two-
Sets of 16.
Yeah. So there's a spinner of first SO16 or spinner of second SO16 will differ between NSR and RNS.
Why does it matter?
Because there are two gauge groups, right? There are two gauge groups. So it does matter as to whether it's the spinner of the first and vector of the second, adjoint of the second, or the spinner of the second and vector adjoint of the first, right?
As a target space theory, should I call this something like quiver?
Well,
Then we have two different gauge groups.
Well, you can call it, but even that name is too big for this, I think. I mean, you don't need to use any quiver language for describing this, right? And just based on this, you should be able to check that you get these extra 128 massless spinners, massless states, right? In the spinner representation of SO16. And that makes 120. Adjoint is the same, right? As we have discussed. We get an adjoint plus spinner, which makes it into 248 massless states. Okay, and that makes it into into 8 adjoint. Okay, we'll discuss this next time anyway, but you can try to check this. Okay, so I think I'll stop.
Time of the next class.
Yeah, time of the next class you have to probably fix, right? I'll send out a message on the Moodle, right? Next week, we also check the schedule, what the schedule is for next week. Next week and the week after, yeah. Has the schedule come up? Do you know? Okay. 9 to 5:30, okay. Okay, then 5:30 to 7 is when you have to make. Till a few weeks ago, Subrat was saying that nobody has gotten their visa or something. The approval hasn't come. So
I think they
Only
fixed
Indians
that.
are.
they have come.
I think they fixed that.
They fixed that. So approvals have come.
At least the program people.
Okay, okay.
At night.
Morning.
How will you come here at 7:30? How will you come here at 7:30?
Why?
No,
5:30 PM is fine.
Yeah. No, why we make 7:30 to 5:30 to 7:30?
Because we can come here. Waking up is better.
Oh, and you have to anyway come from this.
The lecturer does not want to wake up.
Yeah, how will you come? And we have to.
But we can, if you want to take a 7 o'clock bus, you can finish 10 minutes.